Okay, for the remainder of this module we're going to be looking at fluid dynamics, and to do that we have to think about assumptions that we're going to make in terms of what the flow is doing, how we can simplify it and come up with an equation that we can integrate and solve. And when we integrate it we have to apply some boundary conditions, and this lecture outlines how you're going to do that. So this lecture applies to all of the remainder of the modules because we're going to look at different types of fluid mechanics problems. So most of the time for the remainder of this module we're going to assume that the density is constant, and the only time effectively when we assume it's not constant is when we were looking at engines. And also when we will be looking at steady flow energy problems. So it will be apparent when we can't make this constant density assumption. And viscosity, up till now we've ignored it in terms of heat engines. And for most of the rest of the module we are going to assume it's zero. So this isn't physically correct, but it allows us to analyse simple problems without getting too complicated. And the final 5 lectures we are going to be looking at viscous flows, and this is when we start to look at real physics near walls. Okay, so your key problem in terms of answering questions for this module is to make your flow problem solvable. So you're going to get a paragraph of text, and you need to have the knowledge to be able to simplify it. So you need to start looking through the questions, and you need to try and find the keywords in the question, and you need to know what they mean. And this lecture is really about what these things mean. So generally a problem is three-dimensional, and I'm not going to ask you to integrate anything in 3 dimensions because it gets far too complicated. So what I'm going to ask you to be able to do is take a general problem, a general solution if you like, and then you read a paragraph of text which defines the problem, and you work out how to make it more simple. So one of the key ways is to work out in which dimension of a problem is large. So for instance we've got 2 figures here, and these are 2D flows and 1D flows. So with a 2D flow, effectively one velocity component is 0 or it's not important, and in the 1D flow then there's only two of the velocity components are 0, and you're only interested in one of them. So there are lots of problems where the dimension will be said to be large in one of these one or more dimensions. So in this particular example, what I want you to imagine is the dimension normal to the plane of this slide is large. So what I want you to imagine, this channel is extruded out of the page, and let's say that's the Z direction, and that means pretty much that there's no changes in the Z direction because there's nothing happening in the Z direction. Okay, so that means you can simplify your velocity field and make your equations a bit more simple. So in this particular example in 2D, we can say, well, the horizontal velocity component is a function of the x and the y positions, and the v component of the velocity is non-zero, and it also depends on the x and y positions, but neither of these depend on the z position, and the w velocity, if you like, the velocity out of the page, is 0. And if it's a one-dimensional problem, then you can make a further assumption. You can say, well, there isn't any v component here, so we can neglect that. And furthermore, the velocity, the horizontal velocity, it only depends on one coordinate dimension. So you could calculate this at any x and you'd still get the same result. So you need to be looking through the questions. You need to try and work out how can I reduce the dimensionality, the spatial dimensionality of my problem? Because it's the first step in making something solvable. The next simplification is, how do I make my physics more simple? And so you need to start thinking about what isn't changing in my problem. So the classic one is steady flow. So if a flow is said to be steady, it's not changing as a function of time, and therefore all of the time derivatives in your problem, whatever they might be, are all zero. So if you have an equation with a time-dependent term in it, you can just cross it out, set it to zero, because you're making the steady assumption. The next one, if you're lucky to get this, this is a huge win. So if it's a uniform flow, it means that the velocity doesn't vary in space. So you choose 2 points in space, and the question you pose is the velocity the same at these 2 positions in space? If it is, then the flow is uniform, and you can make some significant simplifications. So a lot of the force momentum problems, you'll assume that you have uniform flow over the inlet or the exit, and this makes your momentum problem much more simple. And the final one is something called fully developed. So this is where, let's say we have a pipe and we have flow going down a pipe, and if the flow is said to be fully developed, what that means is that if I do my calculations at some point x, or if I do my calculations at some point 2x or 3x or 4x, it doesn't make any difference. Everything is always the same. Okay, so if the axis of the pipe is in the x direction, then all the d by dx terms are zero, with the exception of pressure. And so pressure is a special case, and this occurs because there's a viscous stress on the wall of the pipe, and you need a force to push a viscous fluid down a pipe, and that force comes from the pressure gradient. Okay, and the key thing that you can assume if the flow is fully developed is that the pressure gradient, not the pressure, is constant. So it's either going to be constant, and it might be zero. Okay, so generally, if it's fully developed, d by dx is zero, except the pressure, which is a constant, and c might be zero. And depending on whether it's a constant or whether it's a zero, we will be discussing this and explaining this later on in the module. And so that sort of completes our, this completes our sort of assumptions, in the sense of what am I looking for in a question to make my equations easy. Okay, so you've got your problem, you've got your equations, you've made your assumptions, you've got to an equation that you can integrate and find the answer to. So you integrate it, you end up with an integration constant. So you need a boundary condition. You need to set your integration constant. So the remainder of this lecture is about how are you going to apply these boundary conditions. So here we start talking about the physical interpretation of these things. Okay, so the first one is velocity at walls, and we make the assumption that there is a no slip condition if the fluid is viscous. So if it's viscous, it means the viscosity is non-zero. Okay, so what this means is the fluid next to the wall is moving with the wall. Okay, so we have two velocity components relative to the wall. We have the velocity components tangential to the wall, and we have a velocity component normal to the wall. So if you think of the wall as a flat planar surface, and we've got a u and a w and a v velocity, three velocity components in an xy coordinate system with three that are all normal to each other, then two of these components are going to be the tangential velocity components. Okay, so one will be, these will sort of lay on the wall, and then the normal component is the component pointing out into or out of the wall. So the tangential velocity assumption is that the velocity moves at the same speed of the wall. Okay, so if the wall is zero velocity, then the two velocity tangential assumptions are going to be zero, and if the wall is moving in a particular direction, then the velocity component is also of the fluid is also moving with that velocity component. Okay, and so for the normal component, there are two boundary conditions depending on the type of wall. If it's a solid wall, obviously there's no flow through the wall, and so the normal velocity component at the wall is 0 as a boundary condition. And if it's a porous wall, that means that the wall is sucking flow out of the domain, or it's blowing flow into the domain. And normally, if you see a question with this, you'll be told what the wall velocity is, and that's the velocity normal to the wall at the wall, and that will sort of complete your boundary condition assumption. The next boundary is something at the edge of a boundary layer. So we're going to start talking about this at the end of the course, and effectively a boundary layer arises because of the no slip condition. So if you imagine we have a velocity over here that's coming towards this flat plate at this v infinite, so this is the free stream velocity. So when the flow hits the wall, it's a no slip condition all the way along this wall. Okay, so the velocity of the wall is 0 at the wall, and far away from the wall, the flow doesn't know about the boundary, so it's still moving at its kind of free stream velocity. And so the boundary layer is this region that connects the 0 velocity at the wall to the free stream. And this change in velocity with time, with space down the boundary, is called the boundary layer. So sometimes we want to integrate across a boundary layer, and if we're going to integrate across a boundary layer, we need to have a boundary condition at the edge of the boundary layer. So mathematically, we can do it very precisely. We can say, well, as the velocity as you go away from the wall, so this y is the distance away from the wall, and as y gets bigger and bigger, the velocity gets nearer and nearer to the free stream velocity. And we can also say that the gradient of the velocity, so the change of the velocity in the horizontal direction with respect to y, gets smaller and smaller as you get further and further away from the wall. But this is very difficult to apply mathematically. So practically, if you really want to integrate across a boundary layer, you kind of invent a boundary layer, an edge boundary layer, by saying that my boundary layer edge is defined when the velocity in my boundary layer is 99% of the free stream velocity. So you set this on as your integration constant, and then you can go ahead and you can do some calculations. Okay, so the next two slides, you're probably not going to use this very much in part one, but we're going to cover it anyway. Imagine we have two large plates. So we've got a plate up here, it's large in the x direction, and it's large in, say, the z direction coming out of the page. And we've got another plate down here, and we've got a flow between these two plates, and this is what the velocity profile looks like. And you can see there's almost like a symmetry plane here. So if you placed a mirror here, the flow above this plane is a reflection of the flow below the plane. Okay, so if you wanted to integrate across this velocity profile to say, let's say you wanted to work out the mass flow between these two plates, you can do it two ways. You can say, well, I can integrate from this plate to this plate, in which case your coordinate point origin might be down here, and use h as the width of the plate. Or what you can do is you could say, well, I'm going to integrate from the center line to the wall, and then I'm going to multiply it by 2 because this is half of the flow and this is the other half of the flow, and it's the same as the top half. Okay, so if you are going to do the second case, you have to know what the boundary conditions are on the center line. So the boundary conditions on the center line are that zero gradients normal to the boundary at the boundary. Okay, so we can see this from the velocity profile. So effectively this velocity profile comes down at this point and it goes through this boundary at 90 degrees. Yeah, so if I wanted to work out the gradient of the change of u, so that's that direction, with respect to y, or x2 in this direction, then it will be 0 at this point. And this applies to all variables. So if this was a temperature profile, it would do exactly the same. Okay, so the gradient of any variables normal to the boundary at the boundary is always 0. Okay, so if you wanted to write this, it would be du by dy at x2 equals 0 equals 0. Okay, and the second one is that there's 0 normal velocity through the boundary. So this is the horizontal velocity component is u, and let's say the vertical component is v. So that would mean that v equals 0 at x2 equals 0 along this boundary. And it's, you know, if you think about it, it has to be this if this is a symmetry plane. Okay, so this is the boundary conditions for an XYZ system. The next one is if you're in a cylindrical coordinate system. So let's say we've got velocity fluid flowing down a pipe, and we want to work out the velocity profile in the pipe. And what we'll probably do is we'll integrate it, or we'll do the integral from r equals 0, which is the center line, to r equals big R, say, and so big R would be the radius of the pipe. So we need again to know what we can assume at the center line, and in this case we've got a cylindrical coordinate system, so u1 is ur, so that's the velocity in the r direction, and then we've got u theta, so that's the kind of the swirl velocity, and then we got uz, which is the velocity along the axis of the pipe. Okay, so at the axis r equals 0, and there's 0 radial velocity, so therefore it's a bit like the planar boundary in the sense that you can't have any flow through the axis. And the second one is that there cannot be any swirl on the center line. This would give a sort of an infinite angular momentum, and much like the planar boundary, in that the gradient of the axial velocity with respect to r is 0 at r equals 0. Okay, and with these boundary conditions you can do the integrals and you can work out the things that you need. Okay, so these are just a couple of examples to try and illustrate the kind of questions that you're going to find and the thing that you're interested in. So these are questions from the workbook that I've scanned in. So here we've got water flowing through a long pipe of diameter 10 centimeters. So this means you can assume fully developed flow, and you're told what this pressure gradient is. And you know now that this pressure gradient is constant all the way along the pipe, and then you're asked to do some things to work out the stress, and we'll come on to that a little bit later about how you do that. So the key words: long pipe, fully developed flow, and you would also probably assume that this flow is steady, so you take out the time derivatives. Another type of question where you're using a large domain in a slightly different way is this one. So here we've got a big tank and we've got flow coming down this pipe, and it goes out 2 different pipes, and these pipe exits are in different heights, and effectively you haven't done this question yet, but it's really about looking at the hydrostatic head in relation to working out how much mass flow goes down these 2 pipes. Okay, and the question says it's a large tank open to the atmosphere connected to a pipe at its base, and so what is this question trying to give you? Okay, so you know about hydrostatics, and you know that the pressure difference is rho GH, so there's a pressure difference between the height of this tank and the exit of this, and there's a pressure difference between the height of that tank and the exit of that pipe. So what this question is trying to tell you is that the tank's really big, and effectively it doesn't matter how much flow goes down pipe 1, the height of this tank doesn't change because it's big, it's large. Yeah. So that means when you do your problem, you can set up your hydrostatic reference height on the height of the tank, and then you can always work out your hydrostatic pressure differences between these 2 pipe exits, and they'll always be the same because the geometry doesn't change and the height of the tank doesn't change. Okay, so you need to be able to read these questions and try and work out what you're being given, and that's a key skill that I want you to learn. Okay, so we've come across some assumptions, we've come across some boundary conditions, and I've given you a couple of examples. So what I suggest you do is don't try and solve anything, but just gently read through questions from chapters 8 up to 12, and just go through the workbook with a highlighting pen and just underline what you think the keywords are on the questions and what you think it might be doing. Because when we start getting going on the rest of the module, we're going to be answering questions from these chapters, and if you've already worked out what the simplifications are, then solving these questions is not going to be too difficult.